Hello everyone, my name is Sergio Hernández and I work at the Catholic University of Maule in Chile, and today I will be presenting evaluating and diagnosing stochastic gradient MCMC. The motivation for this work is to develop image classification models that are robust to dataset shift and provide uncertainty estimates for their predictions. We implement stochastic gradient MCMC algorithms that are well known for efficiently computing posterior estimates when the dataset does not fit into memory. However, several authors have argued that the standard techniques like affected sample size and potential scale reduction do not account for sample bias and therefore cannot be used to diagnose stochastic gradient MCMC. However, these authors have only used flat models with flat priors in order to estimate the sampling bias. Therefore, in this work we propose to evaluate the quality and efficiency of the posterior samples using standard metrics and diagnose different model choices to provide robust classification performance. We consider a multi-class digits classification problem that consists of 70,000 labeled data points. The model is the non-hierarchical model is a softmax regression model that has softmax activation functions and a multinomial likelihood function. The priors are set as a normal distribution with fixed scale and locations. The hierarchical model is as use normal priors with unknown locations and scales. We first compute a point estimate using a stochastic gradient descent. This not only is used as a starting point for the stochastic gradient MCMC methods, but it also is also used as a baseline for classification performance. Stochastic gradient and Diagnosing dynamics is run by two different chains starting from the same starting point, and we can notice that the R hat values have shown non-convergence for both parameters such as the weight and bias. Also, the expected sample sizes tend to be low compared to the sample size. We now compute convergence diagnostics for the hierarchical model. We use the same starting points from the point estimate compute from stochastic gradient descent, and also each sample we only keep one sample after every epoch, so we are also performing thinning on the posterior samples. Therefore, we can notice now that the R hat values show convergence, and also the expected sample size have grown to acceptable values. The classification performance is comparable to the baseline using a stochastic gradient descent. But now we can notice that the hierarchical model has improved the performance in terms of classification results. The R hat values for the hierarchical model have now shown convergence, and the expected sample sizes have grown to acceptable values. Therefore, the non-hierarchical model was not able to converge for a fixed number of iterations, which might be due to the poor choice of the prior. Conversely, the non-centered hierarchical model improves the classification performance, and the hierarchical prior allows to have more flexibility that also improves convergence. Expected sample size and R hat diagnostics are useful to diagnose stochastic gradient MCMC even when the samples are biased, but don't require extra storage and computation. Thanks.